Welcome to cognitive skill number 1, non-sensory nature of electricity. There are multiple levels of abstraction. Just knowing about the abstraction actually aids our learning. So working with abstractions is not a new thing. The first problem is the type of abstraction that it is. We use the abstraction of text and language every day to talk, communicate, and explain things to each other. So it's not new. Electrical has its own text and language. We call this jargon. So you're going to need how to learn and use the jargon. Also, formula, in other words, maths, and diagrams are also electrical abstractions. The second issue is that there are multiple layers of abstraction that add to the complexity and so the difficulty in learning. For example, one, there's the physics itself, the flow of electrons. So we can't see it, hear it, touch it, taste it or smell it, but it's still there and it is the flow of electrons. 2, the language-based symbol system we use. We use a capital I for current. We use the word amps to describe the units. We use R for resistance or the omega symbol, and its units are measured in ohms. 3, we use diagrams and their associated symbols, and we'll go into that in another cognitive skill in quite some depth and detail a little later on. And then there is the mathematics of algebra and geometry. We're going to use a lot of algebra and geometry, particularly when you get into learning about alternating current. So what about the physics itself? Give yourself the undertaking to learn how the physics works. I'll say that again. Give yourself the undertaking to learn how the physics works, not just remember and apply the modelling systems. Yes, it's important in the short term to understand and remember the modelling systems, but in the medium and longer term, give yourself the undertaking to learn the physics. Students often get these two things confused, but I'll speak about that a little bit more in one of the other cognitive toolboxes. Give yourself the space to learn the physics. Be prepared to take calculated risks that a concept will fall into place and be a little clearer a little later. Constantly challenge yourself and check your understanding. Electrical physics is most often about the characteristics of the current, of the electricity, and their relationships to each other. So the characteristics of voltage, what's the characteristics of current, what's the characteristics of resistance. For example, resistance and current are inversely proportional to each other. As one goes up, the other must come down and vice versa. So we say that the relationship is inverse. So understanding the characteristics and their relationships is very important. 2, language and jargon of electrical. Much of the electrical language or jargon is around naming the characteristic parts of electrical energy, that is, the units. Almost without exception, the characteristics of electricity are simply named after people that helped discover or define some part of the concept in electrical physics. For example, again, the unit of current, the ampere, is named after André Marie Ampere, for example. It's just simply the name of the physicist who helped discover it. So the naming of electrical units or characteristics is a declared abstraction. It's just declared to be so because we call it an amp after André Marie Ampere. The unit's name bears no connection directly to electricity. Once we understand this, we simply have to find ways to remember the name of the unit when it turns in turn its characteristics and its relationships. Most people simply remember by repetition, but for me, I remember by knowing some of the history behind the unit's name. I remember by linking the unit's name not only to the person, but to the person's story. So that's an important skill, to be able to remember. We learn things as humans because we like stories. We actually remember things because stories link things together for us well. 3. Diagrams and symbols. Diagrams and symbols can be a challenge because there is a large range of approaches to both the symbols and the diagrams. I've taught some electrical drawing classes in the past, and I can define without much effort at least 15 different ways that you can do electrical diagrams. So my suggestion is to focus only on 2 basic forms of diagrams to start with. 1, the circuit diagram, and 2, the connection diagram. The circuit diagram is highly conceptualized and concentrates on fitting a lot of information into a small but efficient space. This approach uses abstracted symbols that hint at what they do in reality. Conversely, the connection diagram is more concrete, often showing where the components are actually physically located and how the conductors connect between them. Both are electrically correct, but serve very different purposes. The key here is to practice not only knowing each type, but moving backwards and forth between them. A skill I quite often get my apprentices to do is to obviously take a circuit diagram and connect up the components accordingly. But can you take the connection of the components and draw the circuit diagram? Go the other way around. It's worth practicing moving backwards and forwards between having a circuit and making a circuit diagram, and having a circuit diagram and connecting up the circuit. 4. Mathematics. The first thing we need to understand is that mathematics is an abstracted modelling system in and of itself. It is not the physics. It only represents what the physics is doing. It does model the physics very well, and that is why many students get it confused. If you make the effort to learn and understand the physics, that is the characteristics and their relationships, then how the mathematics models this actually becomes obvious. The first relationship most students learn is one we call Ohm's law. That is, the voltage is equal to the resistance multiplied by the current, or the voltage equals the resistance times the current. The characteristic is, if R, resistance, does not change, then current I is increased, then the voltage must have increased proportionally to cause this. This is because I and V are directly proportional, not because Ohm's law says so. Ohm's law is just a representation of the physics. If the current goes up, the voltage must have gone up. That is the physics. Therefore, voltage is equal to R times I. If you comprehend the physics, the maths model just becomes very clear. So, our take-homes for non-sensory physics. Make an effort to learn the physics itself. The flow of electrons. That's what the physics is. It is difficult because of the reasons outlined, but it will take effort, and you need to make that effort. Take the abstraction skills you already have and apply these to the languages of symbols, diagrams, and the jargon. You already have English skills and abstraction skills in the way we talk and describe and tell stories. Why not apply those to the symbols, diagrams, and jargon we use in electrical trades? And finally, mathematics is just another abstraction tool to manage the physics of electricity because we can't see it, hear it, touch it, taste it, or smell it. Yes, learn the basics of algebra and geometry, absolutely, but not in and of themselves, but so you can apply these to electrical physics. I hope you enjoyed our first cognitive tool, the understanding that electricity by its very nature cannot be directly sensed. We're going to always be dealing with it in an abstracted sense, either through meters or watching it light up a lamp or some other phenomena, but we will never actually get to directly see, hear, touch, taste or smell electricity.